All right, guys, so time to talk about calorimetry and specific heat. So we're going to jump right in um, to our PowerPoint for today. And as always, you'll be able to find this on SaintsNet as well. Oops. Let's try that again. There we go. Okay. So let's talk about thermodynamics and specifically about calorimetry. So, what is calorimetry? Well, calorimetry is the study of the measurement of heat flow. So, we're measuring metry, heat flow, calorie, and we use this to determine the enthalpy change of a reaction. We cannot measure enthalpy directly. So we have to measure it indirectly, and we measure it by measuring its change. So when we do calorimetry, we use a calorimeter. We usually measure the change in temperature of a known quantity of water in a calorimeter. Sometimes we measure the change of the calorimeter itself. We have two main kinds of calorimeters. We have one that looks like this that's called a bomb calorimeter. And in a bomb calorimeter, it's at a fixed volume, and so it is not necessarily a fixed pressure. And the one that we more commonly use in our classes and in most college classrooms is what's called a coffee cup calorimeter. And this one is at a constant pressure, but not necessarily at a constant volume because gases can expand and escape through the lid. So before we jump into heat, specific heat and to calculating heat exchanges, let's talk about our units. So we use the joule to measure heat. A joule is a Newton meter or a kilogram meter squared per second squared. And that's the one we'll use most often is either a joule or a kilojoule. Calories, you guys are familiar with in your everyday life. They are a calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And that was defined that way before the joule became the common SI unit. Calories are still used, but they're not the SI unit or the metric unit, although they are 1 gram of water by 1 degree Celsius. The calories that you're familiar with from your everyday life are actually kilocalories. So every calorie on that bag of chips is actually 1,000 calories. And 1 calorie equals 4.18 joules. And then the last unit that you'll sometimes hear in your everyday lives is a British thermal unit or a BTU. And it's the heat that's required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And so a BTU is actually a much larger unit than either a calorie or a joule. And we use BTUs when we're looking at the heat output of stoves or furnaces or even grills. So you'll encounter those occasionally in your everyday life. All right, so let's define a few terms. We talked about specific heat in class today. It is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And both of those are exactly 1 gram and exactly 1 degree. So a specific heat has as many significant figures as is given to you. Now, the difference between specific heat and heat capacity is that specific heat is talking about 1 gram of a substance. Heat capacity is talking about an entire system. So you might hear that the ocean has a really high heat capacity. We're not talking about per gram of water, but the ocean itself. And we also have a unit called molar specific heat, where it's the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius instead of 1 gram of that substance. And so in order to convert from specific heat to molar specific heat, you would simply multiply by molar mass. Okay, so if we think about our definition of specific heat, we've said it's the amount of heat required to change 1 gram of a substance by 1 degree Celsius. And so we can define specific heat as the heat transferred divided by the product of the mass times the temperature change. And this rearranges itself into the equation that you're much more familiar with of Q equals M times C times delta T, where delta T is the change in temperature, C is specific heat capacity, M is the mass, and we're going to talk about, it's very important to recognize whether we're talking about the mass of the system or the mass of the surroundings. And Q is the heat lost or gained. Most often when we do calorimetry, we're actually measuring the temperature change of the surroundings, not of the system. And so we want to make sure that we are talking about the mass of the surroundings, not the system. And then, of course, if we are measuring the temperature change of the surroundings, then this would be the Q of the surroundings, not of the system. But because we know that those two things are equal and opposite, we can use the heat change of the surroundings to tell us about the heat change of the system. So let's do a quick practice problem. With copper, so we have this problem where we have 50 grams of copper that are being heated from 55 degrees Celsius to 100 degrees Celsius. We're given the specific heat of copper and we're asked to calculate the quantity of heat absorbed by the copper. And then the second part of the question asks, what temperature change would the copper cause if it were dropped into 50 grams of water at 21 degrees Celsius? So let's stop for just a second and then let's share our visualizer here. Okay, so when we go to solve a heat problem or a calorimetry problem, we're going to use that equation. We're given a mass, we're given an initial temperature and a final temperature, and we're given a specific heat. And we're asked to find the heat that's absorbed by copper. So anytime we're asked to find heat, we know we're looking for Q, and we're going to use the equation Q equals M times C times delta T. And so Q is what we're looking to find. Mass is going to be the mass of the copper, so we have 50 grams. C is the specific heat of copper, so that's 0.385 joules per gram degree Kelvin. Now, because this is a change in temperature, changes in temperature of Celsius and changes in temperature of Kelvin are the same. And so even though this is given in joules per gram Kelvin, we don't have to convert because the temperature change is the same. So Kelvin, and then we have a change in temperature. So we always want to do final temperature, 100.0, minus initial temperature, which is 55.0. And because it's a change, I'm just going to call that Kelvin because the change in Kelvin and the change in Celsius are the same. So 50 times 0.385 times 45 gives us 866. Now the grams cancel out, Kelvin cancels out, and we're left with joules. This has three significant figures. This has three significant figures. This also has three significant figures. So we know that 866 joules of energy are absorbed by copper. Now, our second part of our question tells us that we then dropped that copper at 100 degrees Celsius into 50 grams of water at 21 degrees Celsius. And it asks, what temperature change does it cause? So now I know I'm looking for a delta T, and I have a mass, and I have an initial temperature. I probably need to know that the specific heat of water is 4.18 joules per gram degree Celsius. So I'm looking for a temperature change, and it says, what temperature change does it cause? So I read this to tell me that it's asking about the temperature change of the water. So here's what I know. I know that the copper's temperature is going to go down. The copper is going to lose energy. I know that the water's temperature is going to go up. The water is going to gain energy. And I know that the energy change of copper is going to be equal and opposite of the temperature change of the water. energy change of the water. So I have the mass of copper times the specific heat of copper times the temperature change of the copper is going to equal the mass of the water times the specific heat of water times the change in temperature of the water. And so I have 50.0 grams times 0.385 joules per gram degree Celsius times the temperature change of the copper is equal to 50 grams of water times 4.18 joules per gram degree Celsius times the temperature change of water. And so I know as well that the change in temperature of the copper is equal to I don't know the final temperature, minus 100.0 degrees Celsius. And I know that the change in temperature of the water is equal to the final temperature of the water minus 21.0 degrees Celsius. I don't know what this final temperature is, but I do know that it's the same. And so now I have two variables, but I can plug these in here and have only one variable. I'm going to go ahead and get rid of the 50 just to make the math a little bit easier. So I have 0.385 times final temperature minus 100 equals 4.18 times final temperature minus 20. So now it's just an algebra problem. Okay, so now we're just going to solve for TF. So 0.385 plus 4.18, and we have 4.565 times final temperature equals 126.3, and now we're going to solve. And we get that the final temperature is equal to 27.7 degrees Celsius. So we know that the final temperature of both the water and the copper is 27.7 degrees Celsius. And so we know that the temperature change of the water is 27.7 minus 21, which is 6.7 degrees Celsius. And we know that the temperature change of the copper is 27.7 minus 100, so it's 72.3 degrees Celsius. Negative. So that's how we would find temperature change. The most important thing as far as writing these is always going to be recognizing that the temperature change is going to be different, but the energy change is going to be equal and opposite. So you want to make sure that you have that negative sign there, which I had left out when I first started writing the problem. So we want to make sure that we have that in our equations. Okay, so back to calorimetry. We're almost done with this section. Okay, so the calorimeter itself We've talked about you can either have a coffee cup calorimeter. This is a simple calorimeter. We're indirectly measuring the heat change for the system by measuring the heat change for the water in the calorimeter. We can use that equation Q equals mCp delta T, or Q equals mC delta T. We will occasionally run across a problem where we're working with a sealed bomb calorimeter. So in a bomb calorimeter, the same process, you're using the heat absorbed or released by the water to approximate the enthalpy change for the reaction. The big difference with bomb calorimetry is that because it occurs at constant volume, it is not necessarily constant pressure. However, the difference between internal energy and enthalpy is small enough that we can usually ignore it. Always, always, always with a calorimeter, we want to make sure that we remember that we are measuring the change in temperature of the surroundings. So the sign of Q is opposite of the system. Usually, if no work is done, we can assume that the delta H of the reaction is equal to Q, that energy that's being given off, that energy that we're measuring. But a delta H reaction is always measured in energy per mole. So we need to divide the energy that's given off by the number of moles that are reacting to find the delta H of the reaction. So one more practice problem. And we're going to switch screens again. Okay, so in this practice problem, we're told that we have a 0.5865 gram sample of lactic acid, and it is burned in a calorimeter. And our calorimeter contains 1.00 kilograms of water. And the temperature of the calorimeter goes from 23.10 degrees Celsius to 24.95 degrees Celsius. And we're asked to calculate the heat of combustion of lactic acid. So first thing we're going to do is determine the enthalpy change, the heat change, or the heat given off by the reaction. So we're going to use Q equals M times C times delta T. Now, remember, we are measuring the energy change of the surroundings, not the system. So this mass that we're putting in here needs to be the mass of the surroundings, which is this 1 kilogram of water. And so we know that Q is equal to 1,000 grams times the specific heat of water, which is 4.184 joules per gram degree Celsius, times the change in temperature, which is final temperature, 24.95 degrees Celsius, minus initial temperature, 23.10 degrees Celsius. And so we get that our energy change is 7,740 joules. This has 4 significant figures, this has 4 significant figures, but this difference only has 3. We get 1.85, so this answer can only have 3 significant figures. So that's the heat that is given to the calorimeter. So we know that the heat that is given off by the lactic acid is equal and opposite. So that would be negative 7,740 joules. But the question asks for delta H of the reaction, or of combustion, which is the same thing. And we know that that is equal to the heat given off per mole. So we need to get this in heat per mole. So we have 0.5865 grams of lactic acid. So we're going to need to find the molar mass of that to find how many moles we have. And so the molar mass of lactic acid is 90.078 grams of lactic acid for every mole of lactic acid. And so we're going to find our number of moles. And we get that we have 6.511 times 10 to the negative third moles. So we're going to plug in our negative 7,740 joules. We're going to divide it by 6.511 times 10 to the negative third moles. And we get three significant figures. 119 times 10 to the sixth joules per mole. Now, you very often see enthalpies of combustion or of reaction written in kilojoules. So you could write this as 1.19 times 10 to the third kilojoules per mole, but you don't have to do that step. Okay, so that's calorimetry. As always, if you have any questions, please let me know.